Welcome to Study Loop.
Okay, what we want to do is determine the number of moles of oxygen atoms in each of the following compounds. So we are starting with, the first one is 4.88 moles of H2O2. So we know that there's 2 moles of oxygen atoms because of the subscript to every 1 mole of H2O2. So if I have 4.88 moles of H2O2, and I know that I have 2 moles of oxygen for every 1 mole of H2O2. So basically, I'm comparing the subscripts of oxygen to the coefficient of the entire compound. So these moles cancel out, and I'm left with moles of oxygen. So as my units, which is what I want, and so 4.88 times 2. So I have 9.76 moles of oxygen atoms. Okay, and basically we're going to just do the same thing with every single one of the compounds. So now I have 2.15 moles of dinitrogen oxide, and I want to know how the number of moles of oxygen atoms. So I do the same thing, 2.15 moles of dinitrogen oxide, and I compare. So I have 1 mole of oxygen to 1 mole of dinitrogen oxide. So that means I have 2.15 moles of oxygen atoms. Okay, and we just keep doing it for the other compounds. There's a couple more we need to do. So we have 0.020237 moles of, I believe this is carbonic acid, if it's aqueous. And so if I have 0.0237 moles, and I know that I have 3 moles to 1 mole. So I have 3 moles of oxygen to 1 mole. And so I basically take those and multiply those together. So 0.0711. So it's a lot like using conversion factors. And then the very last one is we have 24.1 moles of carbon dioxide. And so that means I have 2 moles of oxygen atoms to 1 mole of CO2. So that means I have 48.2 moles of oxygen atoms. So coefficients and subscripts play an important role in the compound.